Okay, so we have equation 29, which is the degree of polarization. That is V, and that's equal to IP divided by IP plus IN, where IP and IN are the constituent flux densities of polarized, unpolarized, or natural light. Unpolarized or natural light. Okay, and considering that expression, we need to write an expression for the randomly polarized density component, IN, of a partially polarized beam in terms of Stokes parameters. Okay, so let's do that. We know that the sum of IP and IN is the incident radiance. So I is the sum of IP plus IN. And for a partially polarized light, the degree of polarization, that would be equation in your book in the section that talks about Stokes parameters. There's an equation, one second here, let me find it. Yeah, there's an equation that says that this is equation 848 in the 4th edition, that V is equal to those parameters. So S1 squared plus S2 squared plus S3 squared square root all over S0, where S0 through S3 are Stokes parameters. And if I label these equations A, B, C, from A and C I get that IP, so I'm gonna plug this in here, so I will get I, so A and C, that's gonna give me S1 squared plus S2 squared plus S3 squared over S0, that's equal to IP over IP plus IN, and from this equation B here, I could say that IN is equal to I minus IP, and now from 1 and 3 we get that IP or first I has to equal as 0, and IN, so replace that with S1 squared, S2 squared, S3 squared square root over I is equal to IP I'm trying to get to IN, yeah, let's do trying to get to IN, so IP is I minus IN over I minus IN plus IN. So these two go away because IN minus IP is I minus IN. Yep, that's true. So now that these two go away, I get my I n to equal I is just as 0 plus move that to the other side, s1 squared plus s2 squared plus s3 squared square root. So this is the expression for IN. So this is the expression for the randomly polarized flux density component of a partially polarized beam as a function of Stokes parameters. Now it says add a randomly polarized Stokes vector of flux density 4 to an R state flux density 1 and see if you get IN equals 4. Well, let's check it out. For a randomly polarized beam of flux density 4, what would the Stokes parameters be? So they will be so this is a randomly polarized beam with flux density 4. So what would the Stokes parameters would look like? Well, S0 would be 4, S1 would be 0, S2 would be 0, and S3 would be 0. So if I write this as a column vector, this will be 4, 0, 0, 0. And an R state of flux density 1 that is in the table in your book, table 8.5, the R state, that's 1, 0, 0, 1, another column vector. And now if we add these two per the instructions of the question, so 4, 0, 0, 0 plus 1, 0, 0, 1, we will get, so adding matrices, this is a simple straightforward matrix. We add each cell with its neighbor, so 4 plus 1, 5, 0, 0, 1. So that means so S0 will be 5, S1 will be 0, S2 will be 0, and S3 will be 1. Okay, so let's see what IN is. So we already said that IN is equal to the expression we derived as 0 minus S1 squared plus S2 squared plus S3 squared square root. So if we plug these numbers in, we have 5 minus square root 0 plus 0 plus 1 squared, which indeed will get us 4. So we do when we add the randomly polarized Stokes vector of flux density 4 to an R state of flux density 1, we do indeed get 4 for the resultant wave. We get 4 for the randomly polarized flux density component. That concludes this question.